Hi guys, let's start a new chapter. The new chapter is called circles. So let's quickly revise certain things that we've already learned in circles in the last couple of years. So circle is a closed figure. It has a center. All points on the circumference of the circle are equidistant from the center. So in this case, this is a circle. AB is the diameter. Semicircle is this shape that is here. This is a semicircle, which means half of a circle. O is the center. Radius is OA or OB or any other line from the center to the circumference. Done. Circumference is the outer boundary of the circle. Exterior point, any point which is outside the circle, for example E, F, G, H are all exterior points. Interior point, any point which is inside the circle, for example I or J in this case are interior points. Next, what are concentric circles? Concentric circles are circles which have the same center. So for example, in this diagram that I have marked the center with a blue point, and then all these circles have the same center, but their radius keeps on increasing. Right? So this is now what I'm marking is the radius of these different circles that are here. So circles which have the same center are concentric circle. Equal circles are basically which have the same radius, which means if there is a circle with radius 2 centimeter and another circle with radius 2 centimeter, these are equal circles. If you remember your chapter on triangles, then these can also be known as, yes, if you remember that term where we tried to prove two triangles equal, what was that term known as? Yes, these are congruent circles as well. So these are equal circles or congruent circles. Now what are circumscribed circles? Circumscribed circles are circles which pass through all the vertices of a polygon. In this case, if A, B, C is a triangle, then this circle which passes through all the three vertices of a given polygon is known as a circumscribed circle, and the center of that circle is called a circumcenter. So O in this case is a circumcenter, and this circle is a circumscribed circle. It touches all the vertices of a polygon. In this diagram, if let's say this is point I is the circumcenter of this circle, and it passes through A, B, C and D. This is in the form of a quadrilateral. So a circumscribed circle passes through all vertices of a polygon, and the center of that circle is known as a circumcenter. Perfect. Inscribed circle touches all the sides of a polygon, which means in this case this circle that we have touches all three sides of this triangle. So this is an inscribed circle. So this is inside a polygon. This is an inscribed circle, and the center of this circle is known as the incenter. Now I've highlighted once here, which means if this is a triangle and this circle touches this side at 2 points, this side at 2 points, this side maybe only at 1 point, this is not an inscribed circle because it should touch the sides only once. Perfect. Now let's look at some more terms which we already talked about in the previous years. So what's an arc? Arc is a part of a circumference. So in this diagram they've clearly shown the one marked in red is a part of a circumference, and the one marked in purple or maroon, no not maroon, purple is the other arc which is a part of the circumference. So in this case the one which is the smaller one is known as a minor arc, and the one which is the bigger one which is more in length is known as the major arc. So this is basically a chord. We've talked about a chord earlier. Chord is a line segment which touches or which joins any 2 points on the circumference of a circle. So again, in this diagram, the second one, this is the minor arc, which is CB is the minor arc, and this is the major arc. Usually you would write this as, if this, you would need a point here as well, let's call it K. So this would be arc CKB. This is to define that this is the line that we, or this is the circumference that we're talking about. And let's say this is point L, then the major arc would be written as arc CLB. Good. Now that we basically talked about a few things, let's look at some more concepts that we've already learned. Next, we talk about segment. What is a segment? Segment is a part of a circle bounded by a chord. So in this case, the chord is AB and an arc. So this is the arc that we talk about. So the area bounded by this, or part of the circle area, part of the circle bounded by a chord and an arc, is known as a segment. So the smaller one is minor segment and the bigger one is the major segment. Similarly, a sector. A sector is an area of the circle, part of the circle, bounded by two ends of an arc with the center. So in this case, OB and OA. O is the center, BA is the arc. So there is OB and OA. The area between OB and A is the minor sector, and this is the major sector. Good. So we've talked about arcs, we've talked about segment, and we've talked about sector. We've talked about incircle, we've talked about inscribed circle, circumscribed circle, circumcenter, and circumcenter. Perfect. Now let's look at some properties of a chord, which is what this complete chapter is about. Let's look at the first property of a chord, which is a straight line drawn from the center of a circle to bisect a chord is at right angle to the chord, which means if I draw a straight line from O to the chord AB, which touches the chord at C, and it bisects AB into two equal parts, AC and BC, then I need to prove that angle OCB and OCA are 90 degrees. So that's basically it. Which means, and this proof is in your syllabus, so it could be asked in your not for this year board exam, but it could be asked in your exam. So this is a part of your syllabus. So let's look at this. A straight line is drawn from the center of a circle, in this case OC, to bisect a chord. In this case AC and BC are given equal. So O is the center of the circle, OA is equal to OB because they are the radius. So OA and OB are equal, they are the radius. And AB is a chord, AC is equal to BC. This is given. We need to prove that these two angles are 90 degrees. So let's look at trying to prove these two triangles similar, or no, sorry, not similar, congruent. So in triangle OCA and triangle OCB, point number 5, what I have is AC is equal to BC. This is given. Next is OA is equal to OB, which is a radius of the same circle. Both of them are radius of the same circle. And then the last point would be OC is equal to OC, which is common arm, which means I can prove these two triangles congruent by SSS test. Therefore, by SSS test, triangle OCA is congruent to triangle OCB, which means I will get angle OCA is equal to angle OCB. This is CPCTC. So I have proven one part of it, which means that these two angles are equal. I still need to prove that they are equal to 90 degree. Since AB is a chord, which means it's a straight line, angle around C would be 180 degree. Okay, so let's just write that angle OCA plus angle OCB is equal to 180 degree. This is a linear pair. But since both these angles are equal, which means 2 times angle OCA, which will be equal to 2 times angle OCB, is equal to 180 degree, which means angle OCA will be equal to angle OCB, which will be equal to 90 degree. So this is a very important property that we will use in throughout this chapter, which means if I draw a straight line from the center of a circle to a chord which bisects the chord, then it makes an angle of 90 degree there. Why is it important? Because as soon as I know that this is a right angle triangle, I should be able to use Pythagoras theorem in this. Right, so let's look at the next property. The next property that we have is exactly the reverse of it, which is what we've called it as converse, which we've been talking about. So converse of this property. So in the previous one, what was given was if AC is equal to BC, then what we got was angle OCA is equal to angle OCB is equal to 90 degree. This is what was what we got in the previous one. Now in this case, since it's the reverse, what we'll get is if angle OCA is equal to angle OCB is equal to 90 degree, this will be given. What we'll have to get is then AC is equal to BC. So this is exactly the converse of it. In this case, both of these get changed. What is given becomes what we get, and what is we get is what is given. Good. Well, the proof of this is not in your syllabus, so I will not spend time on it. So let's look at this. The perpendicular to a chord. So from the center of a circle, if you draw a perpendicular onto any chord, then this will bisect the chord for sure. So line from a center which is perpendicular to a chord bisects the chord. Done. Let's look at the next property. We will talk about two more properties before I solve some questions. So let's look at the next property. Next property says equal chords. So this is property 3. Equal chords of a circle are equidistant from the center, which means two chords are given equal, which means in this case chord AB and chord CD are equal. The center is O. We need to prove that they are equidistant from the center, which means OP and OQ are equal. That's what we need to prove. Now to prove this, let's try and construct a triangle which we will be able to prove congruent. So let's join OB, which is the radius of the circle, and OD, which is also the radius of the circle. So let's start trying to solve it. This proof is in your syllabus, so you should definitely know it. Let's start. So join OB and OD. Good. So what we have is, let's see. So if I apply the previous property, OP is perpendicular to AB, which means it's bisecting AB into two equal halves, which means AP and PB are equal. Similarly, OQ is perpendicular to CD, because this is the shortest distance from a point to a line segment, which means it's bisecting CD into two equal parts, which is CQ and QD. So let's just write that down. Since OP is perpendicular to AB and OQ is perpendicular to CD, therefore AP is equal to BP. This is point number 5 for us, and CQ is equal to QD. Right, CQ is equal to QD. What is already given is AB and CD are equal, which means what we'll get is since AB is equal to CD, therefore half of AB is equal to half of CD. In this case, half of AB is AP, which is also equal to BP, which is equal to half of AB, which is equal to half of CD. In this case, half of CD is CQ, which is also equal to QD. So we have all these four sides equal. AP, BP, CQ and QD, all of them are equal. So now let's look at this triangle. In triangle OPB and triangle OQD. Let's see what we get. So point number 9 is PB and QD are equal. PB is equal to QD. This is from 8. What I also have is angle OPB is equal to angle OQD is equal to 90 degree. This is from 4. Right? We've constructed it. Number 11. So I've got an angle equal, I've got a side equal. I need to get something more equal. Any other side or angle which I can prove equal. Let's see, I also have OB equal to OD. Yes, why? Because they are the radius of the same circle. OB is equal to OD, radius of the same circle, which means I have a right angle equal, hypotenuse equal, side equal, which means therefore triangle OPB is congruent to triangle OQD by RHS test. So since these two triangles are congruent, what I get is OP is equal to OQ. This is CP, CTC. This is what I needed to prove. Perfect. So again a very important property of a chord. In case if two chords are of equal length, then they are equidistant from the center. So two chords which are equal length are equidistant from the center. And I hope you realize that I will get on to the next property, which will be again the converse of this. So let's look at the converse of this property. Let me just open the new file, and here we are. So this is the converse of the previous property. In the previous one, what was given was if AB is equal to CD, then what we got was OP is equal to OQ. In this case, what will be given is, this will be the reverse will become now. So if OP is equal to OQ, then AB will be equal to CD. What it means is if two chords of a circle are equidistant from the center, then they are equal. So what we'll get is AB is equal to CD. Now the proof of this is not in your syllabus, so I will not spend time on this, but I will revise this once again. In case in a circle two chords are at an equal distance from the center, then they are equal. If the distance is equal, then the chords are of equal length. Good. Let's try and solve one question before I finish this video. Let's look at question number 1. Question number 1 says chord of a length 6 in a circle. There is a chord of length 6 centimeter. I have already drawn the diagram for you, and the radius of the circle is 5 centimeters. So let me just draw the radius of the circle. In this case, OA or OB. Perfect. So this is 5 centimeter. Let's just mark this. Next, we need to find the distance of this chord from the center. So distance would mean I will have to make this perpendicular from O onto AB. Let's just write this down. Let this point be P. So point number 1, draw OP perpendicular to AB. Right? So since OP is perpendicular to AB, therefore OP bisects AB into two equal parts. In fact, I don't need to write into two equal parts. Bisect obviously means that, which means AP is equal to BP is equal to AB upon 2, which means 6 centimeter upon 2, which is equal to 3 centimeter. So if AP is equal to 3 centimeter and I have a right angle triangle OPA, I can apply Pythagoras theorem. So in a right triangle OPA, using Pythagoras theorem, what I get is 5 square is equal to 3 square plus OP square. which means 25 minus 9 is equal to OP square. Therefore, OP is equal to square root of 16 centimeter. Therefore, OP is equal to 4 centimeter. So what is the question? Distance from the center. Therefore, the distance of the chord from the center is 4 centimeter. Perfect. Thank you so much. Take care. Be safe. I'll see you with the next video. Bye bye.